So when we talk of the operators, addition, subtraction, multiplication, and division, the four basic operators there, we are going to talk about them in relation to these laws. We say that the operator has that property or displays that property if it obeys that law. It actually does what the law says should happen. If it doesn't do what the law says should happen, then it does not have that property. So first of all, commutativity. What is commutativity? Commutativity, as the name here suggests, it's about commuting the operands. Remember, operands are the numbers in the equation in this particular case. So if you move them around, to commute is to move around, or just to move from one location to another. So commutativity, we're saying if we have x plus 3, and then you commute them around so it becomes 3 plus x, does the answer remain the same? So we see here that if the law is obeyed, then the answer should not change, the value should be the same. Commutativity says if you move the things around and you add them, or you multiply, divide, or subtract, the answer should be exactly the same. Now what we see here is that with addition and subtraction, addition and multiplication, this is the case. If you move things around in an addition, the answer remains the same. So we say that they are commutative, addition and multiplication, because they obey the law of commutativity. Whereas subtraction and division, if you move things around during a subtraction, 3 minus 5 and 5 minus 3 don't give you the same answer. So we see that it is not commutative. Whereas with addition, 3 plus 5 is the same as 5 plus 3. Here are some examples. We are supposed now to show or to prove what I've just stated here when I said addition and multiplication are commutative because they display this property. In other words, they obey this law. Let us check. Prove that addition is commutative. You take those four numbers, 2 and 3 and 4 and 5, and you add them together. You get 14. You take the same four numbers, 2 and 3 and 4 and 5, but you swap them around. You change the order. Regardless of how you swap them around, we see that the answer is always going to be 14. Quod erat demonstrandum. In other words, hence proved. This is the proof that you wanted. So it's proved. It's been demonstrated. QED, that's what we simply say. So if you try commutativity with subtraction, we find that we use the same four numbers, 2, 3, 4, and 5, and then we keep rotating their positions or alternating, commuting them. In other words, you see that the first one gives us negative 10, but if you move them around, do the same thing, you realize that the answer is now different. It's now negative 8. You move them around, the answer becomes different again, depending on which number is in which position. So we see here that commutativity is not supported by subtraction. Therefore, subtraction is not commutative. Multiplication, use the same four numbers. You can use any numbers really. What's important, what we're trying to do basically is just to prove that if you shift them around, the answer will remain the same. If that's the case, we say that that operation is commutative, as is the case with multiplication, and we saw that with addition. They always give you 120 regardless of where you place the numbers. Whereas with division is quite a complicated one, so I decided to just use a very simple one there that you'll easily identify with, where we have 20 divided by 5 is 4, but if you switch the 5 and the 20 around, you get a different answer, 0.25. So in order to prove or to disprove, that's something to disprove anything in science. Maths is a science, by the way. What you simply need to do is to show an instance, a single instance, where the rule is not, where the law is not obeyed. So here, just giving two examples, and we see that they give different answers, that's sufficient to say that commutativity is not obeyed here. But when you're trying to prove that it is the case, you may need to use more examples. Even for the subtraction, it will have been okay by just using two examples. If it shows that both of them do not give the same answer, that's all you need to prove. But if you want to prove that it does give the same answer, you should give room for coincidence. So it's possible that it could just be coincidence that they gave the same number, they gave the same answer. That is why you need to use more examples to illustrate. Don't just use two, multiplication and addition. The rule of associativity is about associating, really, as the name says. Associativity, what you're doing is you're now associating binary operations within a longer equation or a longer operation. 3 plus 2 plus 4 plus 5. 2 plus 3 plus 4 plus 5. When you associate, you're basically saying you want these ones to be seen as if they are one thing. You do that by putting them in brackets and giving them precedence. If you remember the PEMDAS or BODMAS, whatever is inside the brackets is done first. It's associated, it becomes one. So we are saying here again that addition and multiplication are associative because they display this property, whereas subtraction and multiplication are not. We prove it by making different associations. Here we have 2 plus, and then in brackets 3 plus 4 plus 5. So what this means is that you do the 3 plus 4 plus 5 first, 2 plus, and then 3 plus 4 plus 5. 3 plus 4 plus 5 are associated, they're put there together. So what this means is that you do, by the PEMDAS or BODMAS rule, you do the 3 plus 4 plus 5 first, which is 12. So you'll then have 2 plus 12 is 14. The second one says you do the 2 plus 3 first, and then everything else. So 2 plus 3 that gives you 5. This was associated. And then you add that 5 to 4 and then to 5, you get 14. The third one says you do the 3 plus 4 first. 3 plus 4 there is 7. So then you're going to say 2 plus that 7 that you got there is 9. You add that to 5, it gives you 14. And the last one says you do the 4 plus 5 first, which is 9. So you're going to say 2. So you're going to say 2 plus 3 plus 9. This should also give you 14. So this is how we prove associativity with addition. With subtraction, as I said, you just need a minimum of 2 where the answers are different. If you get any 2 where the answers are different, that is sufficient to disprove. However, you may just want to go through all of them here, where we are going to start off by saying 3 minus 4 minus 5. Those are associated. What does this give you? 3 minus 4. Remember, with PEMDAS, you start with the brackets, and then if it's the same operation, you go from left to right. So 3 minus 4 is negative 1. You subtract 5 from negative 1. You are left with negative 6. And then from there, you go 2 minus negative 6. If you remember the previous lesson, you've got 2 negative signs, so you replace them with a positive. So 2 minus negative 6 there becomes positive 8. The second one, 2 minus 3, that's negative 1. And then you subtract 4 from negative 1, you get negative 5. You subtract 5 from negative 1, you get negative 10. The third one there, we start with what's in the brackets. That is 3 minus 4. That is negative 1. So you have your negative 1 there. Then you say 2 minus negative 1. 2 minus negative 1 means 2 plus 1. That is 3. And then that 3 minus 5 gives you negative 2. Then finally we have the 4 minus 5. You start with that first. That gives you negative 1. Then you say 2 minus 3. That's negative 1. You have that -1 minus that other -1 there. So you see it's minus negative, that's plus. It's -1 plus 1 is 0. QED. Now, an important thing to remember when proving associativity is you should not, under any circumstance, commute the numbers. The numbers or the operands should remain in the very same order. If you shift the order of the operands, you are now creating a situation where you're testing both commutativity and associativity at the same time. That results in a failed test, a failed experiment, because you are not able to actually test a single thing. The idea here is you're supposed to just test a single thing. So always when you're trying to prove your associativity, make sure that you do not change the position of the operands. They remain in the same place. Only change their positions when you're proving commutativity. Associativity, there you have it. 3 times 4 times 5, that is what, 60. I get it. So you're going to say 2 times 60, that gives you 120. Second one there is 2 times 3, that's 6, times 4, that is 6 times 4, 24. You multiply that by 5, it gives you 120. The third one says you start with the 3 times 4, which is 12. Then you'll say 2 times 12 is 24, times 5 is 120. And then the last one there, you start with the 4 times 5, which is 20. So you'd say 2 times 3, that's 6, times 20, it's 120. QED. So we see associativity there agrees with multiplication. Then finally with the division there, remember you don't change the position of or the sequence of the numbers. What you simply do instead is you change the position of the brackets. The first one there, 24 divided by 6. Then after getting the answer of 24 divided by 6, you divide that again by 2. 24 divided by 6, we see there is 4. Then you divide that 4 by 2, you get the answer being 2. In the second example, the brackets are around 6 divided by 2, so you do that first. 6 divided by 2 is 3. So you'll have then therefore 24 divided by 3, which gives us 8. So we see the answers are different. QED. Finally, we look at the distributivity law. Distributivity law is somewhat different from what we've been discussing there, because now we're just saying we're not trying to prove it, because distributivity only works with multiplication and division on addition or subtraction. Multiplication or division on addition and subtraction. Addition or subtraction. First one there, A times, see that's the multiplication, on in addition, B plus C. What this means is you can either do the BODMAS by adding the B and C first to get the answer, and then multiplying that answer by A. You can do it that way, it'll give you the result. It also has the same result as if you distribute the A to the members of, or to the numbers, to the operation which is inside the brackets. So in other words, you go A times B first, plus that same A be multiplied on the C. The answer should be the same. So I think if we use actual numbers, we'd be able to have a better appreciation of it. Now look at those variables. Look at that, the first one there using variables. We have A on. Remember, if you've got brackets immediately, it means multiplied by. So this means A times or A on B plus C minus D. So the answer that you get by doing the B plus C minus D first, and then doing what? Multiplying it by A, should be the same as if you multiply the A by each of those individuals. Then you do the multiplication there. So I'm picking up that there was a bit of an error there. That's supposed to, the original sum is supposed to be A. Instead of subtraction, somewhere I used addition. So I think the best solution would be to resolve this and change this minus there into a plus, because the rest of it behaves as if this was a plus. So I'll just do that before I note the notes. So if we take the real life examples with literals remember are numerals, numbers, numeric values. So you can have it as 2 times, and then in brackets 3 plus 4 plus 5. If you do it this way, you find that you do the 3 plus 4 plus 5, this gives you 12. So 2 times what was in the brackets there, which is the 12, is 24, using the Bottomless rule or PEMDAS. But if you use the distributivity rule, this simply means you just multiply it, apply that 2 to each of those values. So it becomes 2 times 3. That's what we have here. And then that same 2 that's on the outside, you multiply it by the 4. And that same 2 that's on the outside, you multiply it by the 5. And then that's when you add them up together. So the 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10. You add those 3 together, you end up with 24.
Now here's an interesting example with division. We have here 2 divided by, in brackets, 8 plus 4 minus 10, close bracket. If you attempt to distribute the 2 into the dividend, which is 8 plus 4 minus 10, by 8 dividing into 2, 4 dividing into 2, and 10 dividing into 2, you are going to get quite a complicated answer. The answer you get here is incorrect. This is because you've distributed the dividend rather than the divisor. This is because division is not commutative, so the position of the divisor as opposed to the position of the dividend does matter. So distributivity only works for division if you are dividing by the number that you are going to distribute. Finally, identities, and by extension, inverses. Simply put, an identity for a number is a number which, when operated on another number, does not change the result altogether. Sounds a bit confusing, but listen to this. If you add 0 or subtract 0 from any number, the answer does not change. Similarly, if you multiply or divide any number by 1, the answer does not change. Therefore, we say the identity for addition and subtraction is 0, and the identity for multiplication and division is 1. So any number x plus 0 is going to be equal to x, or x minus 0 is x. Therefore, the identity for addition and subtraction, remember subtraction is a form of addition, is in fact 0. And any number x times 1 is equal to x. Similarly, x divided by 1 is equal to x. Therefore, we say 1 is the identity for multiplication, and by extension, division, since remember, division is a type of multiplication. It is important to remember that there's a difference between 1 and negative 1. So negative 1 is not the identity, rather positive 1 or just 1 is the identity for multiplication and division. The inverse is basically a number which, when operated on another number, will give the identity of that operation. In terms of addition and subtraction, the inverse is just the negative of the number in question. For instance, the inverse of -1 is +1. The inverse of 70 is -70, etc. For multiplication and division, the inverse is what we call the reciprocal. The reciprocal of a number, simply put, is the answer you get when you divide 1 by that number. In other words, the reciprocal of 2 is going to be 1 divided by 2, which is half. The reciprocal of 1/7 is going to be 7/1, or simply put, just 7. Similarly, the reciprocal of a fraction which is made up of other numerals than 1, for instance 2/3, is just the inversion of that fraction, which is, for instance in this case, 3/2. So remember, the identity is what you get when you multiply a number by its reciprocal in terms of multiplication, or when you add a number to its inverse in terms of addition and subtraction. So remember, the inverse for multiplication and division, which is called the reciprocal, is the number which, when you multiply by the original number, will give you 1. And the inverse for addition or subtraction is the number which, when you add to a number, will give you 0. Like this video and subscribe to this channel for more such content.